So all the code for this talk is on GitHub. So I've got a fork of Juice on GitHub here. I had to put this in a different font since this is a 0. And it's in a branch on that GitHub repo under ADC 2016 final. Probably guessed that I had an earlier version that I wanted to delete. So throughout the talk, I've got some examples. Some of this is going to be in the slides. I'm going to switch out of PowerPoint and go into Xcode to do some live examples. First of all, smart pointer containers. This talk is billed as a kind of intermediate talk, so some people that maybe are not super confident with C++ in general, but we've maybe been using Juice. So some of the talk is going to talk a little bit about smart pointers in general, introduce their usage, how the smart pointers in Juice work, but also there are these new available C++ pointers in modern C++ that effectively have equivalent functionality. So, what do smart pointers do? Well, broadly speaking, one of the typical uses is to manage the lifetime of objects and then effectively delete them automatically when you no longer need them. One of the problems you can get with pointers is if you allocate a new pointer to an object, and unless you're really careful, it's quite easy to lose a reference to it and you leak. And particularly in audio applications where you might be creating lots of objects, and if you forget to delete a few of them, and these are happening very rapidly, you're quickly going to run out of memory or some other disastrous consequence will happen. Other than Jules writing Lightfoot, you should probably be using smart pointers if you're not already. Jules's use case in Lightfoot is clearly a very specialized use case. In many cases, and I'll point out which of the ones are particularly low overhead, it's zero cost to use some of these smart pointers. So you may as well be using them as opposed to raw pointers because there's just no reason really not to. The basic premise of smart pointers is don't use delete. If you're using delete in your code, then you could probably use a smart pointer to more carefully manage the lifetime of your object. Ideally, you wouldn't use new, but in the style of the way that the Juice scope pointers work, scope pointers and owned arrays and so on that we'll talk about in the talk, then you do use new to allocate the pointer. In the modern C++ equivalent, then there are some ways of creating these objects that contain the pointer that don't use new, but I'll come to those later. But the main thing is, if you're using delete, have a think about whether you could refactor the code to use some kind of smart pointer to manage that resource more carefully. So, the Juice smart pointers are, or related classes are, scope pointer, owned array, weak reference, reference counted object, and reference counted array. All of these, as I say, you have equivalent ways of achieving the same thing now in the standard C++ 11 and C++ 14. So some of the things I'll look at are C++ 14, some are C++ 11, but it's broadly that kind of notion of modern C++. So let's just look at some typical use of where scope pointers would be seen in live Juice code. This is the sort of code that the producer will generate if you use the GUI editor, for example. So you have a scope pointer or several scope pointers, each holding a pointer to one of these types of objects. So here you can see I've got 2 sliders and 2 text buttons that might be in my user interface. We could, of course, actually at this point just hold the objects themselves, so we don't really need the scope pointers. But that's kind of not the point of the talk. Another thing about the way in which Juice code tends to be organized, this is a kind of idiomatic way of initializing your components, your sliders and buttons and so on within the user interface. This is not quite the kind of code that the producer would generate, but it's the sort of code you will see throughout the library and the demo code and the examples. So here in our constructor, we are allocating a new slider, assigning it to our scope pointer, slider 1, and at the same time, because that whole expression within the add and make visible call returns that pointer as well, we can also add it to our parent component, which then allows it to be positioned within that component and displayed on screen. So that's quite the kind of idiomatic use of juice. So the key point about the scope pointer, as I said at the beginning, is that you can't forget to delete those objects unless you deliberately do something silly. Because as your parent component goes out of scope, those 4 objects in this example will automatically be deleted at the end of the deconstructor. I say you could do something silly. So, for example, there are more sophisticated ways of dealing with scope pointers where you might want to release the object and store it somewhere else. But broadly speaking, you'd have to do that deliberately. So it's kind of the opposite way around to storing raw pointers. You have to deliberately do something to leak the pointer rather than accidentally leaking it. In addition to that, you could manually effectively cause the delete to happen by assigning the scope pointer a null pointer. So it just doesn't happen, but actually this is in the code that I had on the previous screen, but this is the sort of code that actually the producer will generate. Why would you want to do that? Well, it might be that you, for some reason, need to specifically control the order in which the objects are destroyed. There are certain circumstances which that might be useful. So, for example, if the objects refer to each other in some way, then you might need to delete one before the other, and so on. However, given the asterisk point here, it might be that this suggests some kind of other problem with the code, that you've got these over-interdependency between the objects. But if you need to destroy them in a specific order, then you can do it that way. So, the point of the talk is to think, well, how could we not use scope pointers because we've got this new class in C++, standard C++ 11, 14, that we could use instead. So the equivalent in modern C++ is unique putter. So you can see actually the code on the right-hand side there, and there's a reference to the example project on GitHub, is broadly the same. It's the same sort of thing, and it does behave in a very similar way. There are some things that we need to change, which I'll go through now, to get it to work in an equivalent manner in Juice code. I'm using components as a particular example because obviously they're used throughout the library and they're a main ingredient of making user interfaces. So the main thing we can't quite do in the same way is that nice, neat, single call to add and make visible, allocating the object, assigning it to the scoped pointer, and then returning. We can't quite do it in exactly the same way. Things that do work without you having to make any other changes to your code if you're porting over from scope pointers to unique pointers is everything that uses the arrow operator just works, pretty much. I haven't found anything that doesn't. I can't think of any reason why it wouldn't either. Sometimes we might need to call the get function on our unique pointer, in order to get similar behavior. So for example, an example I'll show later is where we need to compare the raw pointer you might get in a button callback. So you click the button, you get a callback button click that says this is the button that was clicked, and you'll commonly go through a series of if-else statements in order to figure out which button was actually clicked that you know about. In those cases, we will have to call get in order to obtain the original pointer in order to do that comparison. But broadly speaking, it's a pretty lightweight series of changes. So there's an example where this will be exactly the same code whether you use scope pointers or unique putters. The constructor, on the other hand, there's one go at it. There's several ways you could do it, but there's one go in that I allocated the objects in the initializer list and then had separate calls to do add and make visible. That's one way of doing it. Could we make it neater? Not without making a few modifications or using more lines of code. So I had a go at thinking about ways we could get around this. Well, one thing we could do, not sure whether this is necessarily the best practice, but one way around that would be we could make a little shim class that goes in between the juice component class and the one that we inherit from. So here's a template function that effectively takes a unique putter of pretty much any type, but we're intending it to be of a component type. And it's a R-value reference. And this is our kind of C++ 11, C++ 14 version of add and make visible, which in turn calls add and make visible, by calling the get function and passing through the Z order, so which order in our series of child components does the new component we're adding get placed. And then we move that back to the caller, which means we can then do the whole thing in one line again, although it's slightly different. It's kind of inside out. So instead of having the equals assignment within the brackets, it's actually outside. So here, again, very similar code, but slightly different. This is in fact using std make unique, which is a C++ 14 standard. So actually in Xcode you have to deliberately enable C++ 14 compiler. In Microsoft Visual Studio 2015 it works without any modifications. Alternatively, we could still call new slider and we'd have a similar kind of result. So, as I said earlier, one of the other places where we'd need to call get explicitly is in a callback. So here's a typical callback for a button clicked, a callback that you would get in Juice code. Same sort of thing applies to any of the types of callbacks for sliders, file name components, and so on. So we get a function that says a button was clicked. You need to figure out which one it is to do something with it. And we compare the pointers. Now, that will work with a scope pointer because scope pointer automatically casts back to the raw pointer in this scenario. But a minor change we'd need to make in the unique putter is to call the get function on our members in order to compare it with that button that's been passed to us. Again, fairly trivial, and it's more explicit what you're doing there, and it's probably a good thing. So one of the other ways in which you can store collections of pointers that are managed by an object is in Juice. We could use the ownedArray class. It's effectively an array of scope pointers. Effectively it isn't, but it's effectively the same kind of functionality. So I've highlighted the two kind of key lines there in yellow, and again the example is number 3 on the GitHub repo. I've omitted some of the code in the middle there with the ellipsis, which is things like positioning it. We've already seen how we do that, and there's a paint function in there that was just putting in a kind of pale background. So the main code there is we're constructing our child components and we're positioning them. So here we've got ownedArray of slider, so that's an array of pointers to sliders. And again, neatly designed in the API of Juice is that we can do that whole thing in terms of allocating it and putting it into the array in one line. As you might guess, we can't quite do it in exactly the same way in C++ 11, C++ 14. Now, of course, I'm deliberately using this type of iteration as well, of using an index to iterate through the items in the array of sliders. Again, if I've got a C++ 11 compiler, I could use range-based 4 in that case, but I'm deliberately using sort of C98, C++ 98 code in these sort of core Juice examples. This is what I mean. So here's the range-based 4 in this C++ 14 example. Again, C++ 14 only because I'm using make unique. And again, this is using my C++, my component CPP11 base class with that function in it that allows us to do this single line call. And in this case, we're using std vector of unique putters to sliders. Again, in C++, minor note, in C++ 11, we don't need to put a space here, but slightly annoyingly in C++ 98, you have to put a space after the second angle bracket, or it misinterprets it, mispasses it. And in this case, we use in place back. So actually what happens is the unique pointer is moved rather than copied. It's moved onto the vector. So again, relatively minor changes as long as we've got that little helper class, or we could implement it as a function instead of having it as a base class. But we've got this helper function that allows us to do in similarly neat lines of code. So that's the kind of basic principles, and using a very simple example, which is unique putter and scope pointer as the way of discussing it. There are other classes in Juice that allow us to do very similar things in different scenarios. So these are some of the other objects I mentioned earlier, or classes that I mentioned earlier, that allow us to deal with what we call smart pointers. So there's weak reference, which allows us to store a pointer to an object, but we can also find out when it's been deleted. Reference counted object, so we can store an object in multiple places and we can automatically have it deleted when all of those references have gone away. And the equivalent, which is an array of them. So the equivalents to those, not completely comparable, but the equivalent functionality, which I'll talk through in the next examples, would be these in C++ 11.14. So we can get similar functionality to weak reference with weak pointer, weak putter. And we get similar functionality with reference counted pointer, reference counted object, and shared putter. And reference counted array, we'd just use a vector of shared putters, or something along those lines. But there are quite a few differences in these cases, perhaps more differences than there would be with unique putter, which is very, very similar to scoped pointer. So, purpose of a JUICE weak reference, as I say, is to hold a pointer to another object. But what could happen if you were just storing a raw pointer is that object could get deleted by something else. And you wouldn't know about it, and you could end up dereferencing it and end up in a terrible mess and a crash. The point being that you can always obtain the original pointer from the weak reference, but if it's been deleted in the meantime, since you assigned it, then you get back null pointer. So you can test for that condition and then not do something really dumb like dereference a null pointer, because obviously that's going to crash as well. So we can avoid having to avoid dereferencing an object that no longer exists, but we need to explicitly, obviously, not dereference null pointer. So, equivalent in C++ 11 would be stud weak putter. But slight problem with that is that for stud weak pointer to work, we need to actually use something else called shared putter, which I haven't talked about yet. Shared pointer is actually this thing that stores stores a reference count of how many of these objects exist, and when that reference count drops to 0, then it can be deleted. JUICE has this separate notion of a weak reference that doesn't really need to interact necessarily with shared putters. So it is quite a different mechanism. So let's just look at an example where this might be used. So I'm going to come out of the presentation. And look at this weak reference example. The one thing I forgot to change, actually that's usually not readable. It's such a massive screen. Is that all readable even at the back, Chris?
It's all right.
So that's probably quite good because I can get more of it on the screen. Okay, so it's slightly contrived, as many of these kinds of examples might be, but I came up with an example that will illustrate why you might use a weak reference. If you were writing some kind of library function where you wanted to maybe flash the color of a particular component to a particular color that you select and then go back to its original color, then you might use something like this class I've written here as a simple example called component color highlighter. So you pass it a component, you tell it what color to go to, how long to stay on that color, and then it will revert back to the original. Of course, the problem would be is if this class here was to hold on to the raw pointer and the original component got deleted in the meantime, as it tried to set the color back to its original color, you get a crash because the object's gone. So I'll show you what it does. So we've got our simple interface with a couple of sliders, a couple of buttons, and what should happen as I drag the slider, its thumb will go red for a short while, and then it will get switched back to the original color. So kind of useful. We could have achieved this behavior, I know, without using this special class that I've written, but I'm trying to illustrate the point of why you would use weak references, or places where you might need to use it. Of course, if we were deliberately just trying to change the color of this and put it back, then we could just use a timer in our component class. But if we're trying to write something that's generic that can be used in other places, then this is a typical type of solution that we might use. So this is the key place where the the weak reference is held. So in our array of things that we're holding in terms of objects that have been highlighted, then we store its original color as we put it in. We store the weak reference of the component rather than the original component. We can store which color ID we changed, so we could flash any of the colors, background, thumb color, track color, in terms of sliders and so on. And in fact, with the button, I'm flashing the text instead. And as the timer callback happens, this is the critical place where we try and get our original component back out of this weak reference. So it's this line here, line 75, where we try and get our comp, which is a weak reference, back to our original comp. And that if statement will evaluate to null pointer if the component's been deleted in the meantime. So we won't end up doing the following line, which would otherwise crash because the component's gone. So, I mean, I'd have to really contrive this to make the component disappear, but you can imagine scenarios where you might have things that pop up and go away. So in this example, I'm just going to make this button disappear. Button number 2 will disappear if I click on it. Now, if I hadn't used a weak reference, at the point when I click on this button, it would crash. But in this case, it doesn't. It continues to run, and everything else still works. So we've managed this by not trying to set the color back to whatever the original color is. So we'd be putting the color back to black text from the red, in the case that the object's completely been disappeared. So we're using a weak reference to do that. So the equivalent in C++11. So the next example, number 6. As I said in the slides, then we can't quite do it in the same way, or in a completely equivalent way, because we can't use unique pointer in this case, because we can't get a weak reference to a unique pointer in C++11 or 14, because it's a really lightweight object that's deliberately there to make it zero cost, as I mentioned in the very beginning. So in this case, we're going to have to use this thing called shared putter. So we're storing it in shared putters, and instead of storing a weak reference, again, that line there, we're going to store a weak putter to the component. But broadly speaking, beyond that, the code is pretty much the same. So in this case, instead of getting back the original component, we actually have to convert our weak putter back to a shared putter. And in that case, it will be a null pointer shared putter if the object has been deleted in the meantime, which again, we won't bother. The code then won't move on to this line here, line 77 and 78, in terms of trying to reset that color back to its original. So again, we get the same sort of behavior using the standard library functions. So again, colors highlight on green, button goes red, and this one will delete it, but it magically doesn't crash in this example. So there's another example where we can use the same sort of functionality, but using standard library classes to do it, to achieve it. So let's just close these down. Okay. So actually moving on to reference counted object and actually shared putters proper, for using shared putters for what they're really designed for, rather than just being able to have a weak reference to them. Just a quick introduction. Many of you will know what reference counted pointers are, but again, as an intermediate talk, it might be that you'd not used them before. So the idea is that you can store your pointer in multiple locations, and the object tracks how many of those references exist, and when it drops to 0, they get deleted. A typical example of how you might use it would be for some sort of garbage collection, and I've got an example to show you shortly. The examples are based on this tutorial here, which is on the JUICE website. It's Tutorial Audio Sample Buffer Advanced. Basically the idea, if again we switch back to Xcode, is that it loads an audio file, loads it into a buffer, and then starts to play it in a loop. The idea being that we can then load another file which will overwrite the existing one and play that one instead. Now we need to be a bit careful with this, and this is one of the areas where shared putters can be really useful, in that we need to be careful not to call new or delete on the audio thread. So we've got the critical bit of this code here. I'm not going to go through every line of this. You can go back to the tutorial online to review that. But essentially what's happening here is we're pulling the samples out of the buffer and playing them back and looping back around to the beginning. The important bit is at the top here that we store in our class a reference to the current buffer that we're playing, and by storing it in a local variable here, that bumps the reference count by 1. So it means that it can't be deleted, at the very least, until this point. The problem will be, though, could be, that if somehow, while this function is running on the audio thread, that the buffer gets changed, then it could be that the old one gets deleted here, invisibly. I refer you to Timo's various talks at CPPCon and so on in terms of audio software development. This is one of the kinds of examples that he illustrates. And the almost invisible problem you might get in this scenario would be having an object deleted on the audio thread almost without you noticing it, which could cause glitches and is generally bad practice, is calling delete on the audio thread, because it takes an indeterminate amount of time, or could take an indeterminate amount of time. So how do we manage that? Well, what we could do is we can manage a pool of objects. This is actually reference counted object pool is actually a type def. So what I've got here is effectively a reference counted array of reference counted objects. So as we open a new file, we store it in our current buffer variable and we put it into the array. And then we can play it, and then when we put a new buffer into or we select a new buffer, or load a new buffer from disk, then it also switches the current buffer and also puts it into the array. So all that's left to do, using this kind of poor man's garbage collection, is to iterate through that array and find out if any of those references have dropped sufficiently low, effectively to only 1, and then at that point we can then remove it from the array, which will cause it to be deleted. Now in this case, a lot of this code is actually just there to check that it's actually working. So in fact, here what I'm doing is I'm passing in a name for the buffer to use. You don't really need that, to be honest. We probably just need the buffer. But I'm putting the name in so we can actually include this debugging code to actually see, as we're running the code, we can see it actually happening. We can see when it's deleted and so on. So if we run this example, okay, so we've got a couple of files. One thing I didn't check either was audio, but it's coming through HDMI, so it should work. Okay, we won't have too long of that. But we could see the points at which these things were created and destroyed as we selected them. The key thing that none of that deletion happened on the audio thread, in that we've got a separate thread that's actually running both the loading, so it's this run function here that's sat in a continuous loop that is checking whether we need to open a file and also whether it needs to free any of the files. So this is the loop here. So in this case, our reference count would end up as 2. So actually, probably unnecessary, but I took an extra reference here. So there's 1 in the pool, and there's one reference in this local function here. So if at this point our reference count has hit 2, we know that the current buffer isn't this one, it's something else. So we can safely, at this point, remove it from our array, which will ultimately, at this point, as it exits the scope of our, well, actually it exits the scope of the if at this point, it will then actually cause it to delete, which is where we see this destroyed function here happening in the log. So, how would we achieve a similar thing with the C++11? Again, very similar. I won't subject you to the sound. I'll just show that it does the same thing. Again, I'm using here type aliasing rather than type def as a more modern way of using a different name for a type. And in this case, you'll see that actually, although we were doing a similar thing in the previous example, we're actually storing a shared pointer to void. What this allows us to do is actually start our pool, so our shared void pointer pool can effectively store any type of object. So we could use it to garbage collect any type of object that we decide to use within our application. We don't have to have a dedicated pool for each object unless we really have another reason to do that. But it effectively does the same thing. We're using shared pointers, and we're using a vector of shared pointers to void for our actual pool. But the code is broadly the same, although I've used this arrays if technique here. However, I haven't got any prizes to give out, but I'd be curious as to why actually it needs to be 3 and where those 3 references are. In this case, I know that there's one reference here and there's one reference in the pool, but there must be a third reference because it has to be 3 for this to be valid. But maybe if someone who knows more about how arrays works or how remove if works, it may be that it's also storing an extra reference internally. But this effectively does the same thing. This iterates through the pool and finds pointers with ref counts that are 3 and removes them from the pool in those instances, which again yields us to delete it at the point when we need to, but not in the audio thread. It's on our special worker thread that's doing the file loading and file deleting. Okay, so shared pointers and reference counted objects, broadly equivalent. We can use them in roughly similar ways, but there is a slight difference. One of the clear differences actually is as a positive is that actually for a shared pointer we don't actually have to inherit from a class in order to get this reference counting behavior. We can put any object in a shared pointer. This is because the reference counting works in a different way. In Juice, reference counted object is known as an intrusive count, an intrusive reference count, in that the count's actually stored within our object itself, whereas shared pointer stores it separately. One of the problems that this results in is that what we can do in Juice is we can pass a this pointer out and store it somewhere else in another reference counted object, and it will safely increase and decrease the counts. We can't do the same thing with shared pointer because it has this separate count. So in order to get similar behavior, and this is quite a specific use case, but we'd have to inherit from enabled shared from this, and we'd have to use shared from this to get our this pointer instead of actually using a raw this pointer. So that's a minor difference, but quite important. One of the other questions you might have is, well, what's the performance? Now this is micro benchmarking, and it's only done on this machine, but as I say, I've got the code on GitHub, so I welcome you to sort of try this on various CPUs and compilers. The tests I've run are in sort of 3 sets. One is comparing effectively scope pointer and unique pointer. You can't compare all of them against each other because they're doing different things. Effectively, for example, in this top example, I'm generating 2 random numbers and storing them in 2 unique pointers, and then adding the result and returning it and printing it to the console to make sure the optimizer doesn't do something silly like optimize it away and not actually do it. So it is actually doing the code. And you can see the performance is rather similar. This is running 10,000 iterations. It's bootstrapped, so it randomizes the order of the tests. So I'm fairly confident that these are good results. So roughly similar, but you can see minimal performance needed. In terms of comparing reference counted object and shared pointer, during the review process of the conference, there's one of the reviewers suggested that actually one of the reasons that Jules has held on to the reference counted object for so long is that, well, not only is it needed for C++98 compiling, but it's all been shown to be faster than shared pointer. Well, and again, this kind of shows that that's perhaps true, in that, again, these are performing the same sorts of operations over many, many iterations, and reference counted object is performing better. I tried two different versions actually, because I had to write obviously with Juice, I had to write a class to store my int. I can't just stick an int into a shared pointer. Well, I can stick an int into a shared pointer, but I can't just stick an int into a reference counted object. I actually have to make a class that stores an int, and so on. So I tried different versions that have all of its operators are inline, all its methods are inline, and one where they aren't, or they're not marked as such. It might be the compiler decides to inline them. And you can see that the performance, it probably is, because the performance is roughly similar, but you can see that it outperforms in terms of doing exactly the same operation. So that might be a reason to actually hold on to using Juice smart pointers in this instance, particularly in high performance code. This last one was the one that I thought, this is going to blow them out of the water. It's going to be definitely much less efficient to use a shared pointer to a component compared to just using a weak reference. Thinking being that the component's always doing the weak referencing. So it's doing both. And even doing both, they roughly perform very similarly. So, as a quick overview, we looked at some of the smart pointers available in Juice. We have an introduction to some of those, particularly scope pointer, a reference counted object, with the example code on GitHub. And compared those and looked at how you can port over that code into standard C++11, C++14, and some of the differences and some of the particular pitfalls that you might come up against when trying to, or whether you'd want to move over to use these modern C++ idioms. Okay, so take any questions.